When Pluto was officially reclassified as a dwarf planet in 2006, it felt like a final decision, a quiet closing of a chapter in humanity's map of the solar system. Once considered the ninth planet, it was reduced to a technical classification. A distant object. A frozen remnant of formation. Something no longer central to the story of planetary evolution. For a long time, that interpretation seemed stable. Pluto was described as an ice world at the edge of the Sun's influence, a place so cold, so distant, and so isolated that geological change seemed impossible. A dead world. A static world. A world finished long ago. But that idea is now breaking apart. Over the last decade, and especially with refined data from deep space missions and advanced infrared analysis, Pluto has begun to reveal something unexpected. It is not static. It is not inert. And it is not simple. It is active. Not in the explosive, volcanic sense of Earth, but in slow, persistent, internal motion that continues even in extreme cold and distance. At the center of this realization lies a massive region known as Sputnik Planitia. A vast, heart-shaped basin dominating Pluto's surface. At first glance, it appears frozen and still. A pale scar carved into an icy world. But closer analysis reveals something far more complex. The surface is not fixed. It behaves dynamically. Composed primarily of nitrogen ice mixed with methane and carbon monoxide, it flows over time like a very slow glacier. Layers shift. Material circulates. Older terrain disappears while new patterns emerge. This is not geological death. This is geological persistence. Even more surprising is the way Sputnik Planitia appears to influence Pluto itself. Its immense mass creates a gravitational imbalance strong enough to affect the dwarf planet's orientation. Pluto is subtly tilted by it, locked into a stable alignment where this massive basin always faces a consistent direction. It is as though the planet carries a permanent weight, shaping its motion through space. But the surface is only the beginning of the story. Beneath the ice, scientists now suspect something even more significant. A subsurface ocean. Hidden beneath tens or even hundreds of kilometers of frozen crust, this ocean would not resemble anything familiar on Earth. It would be dark. Pressurized. Completely isolated from sunlight. And yet still liquid. The only reason such a structure could exist so far from the Sun is internal heat. Radioactive decay within Pluto's rocky core releases energy slowly but continuously, providing enough warmth over billions of years to prevent complete freezing beneath the surface. This changes everything. Because liquid water is one of the most important ingredients for life as we understand it. Not life itself, but the condition that makes life possible. If Pluto contains a subsurface ocean, then it is no longer just a frozen relic. It becomes part of a growing class of ocean worlds in the outer solar system. Worlds like Europa. Like Enceladus. Bodies that exist far beyond the traditional habitable zone, yet still contain liquid water. Evidence supporting Pluto's internal activity first became clear during the New Horizons flyby. The spacecraft revealed a surface shaped by fractures, ridges, and tectonic patterns. These are not random features. They are structural signs of movement beneath the ice. A crust being stretched, compressed, and slowly reshaped from below. This suggests a world that is not frozen solid internally, but still evolving. Even Pluto's relationship with its largest moon adds another layer of complexity. Unlike typical planetary systems, Pluto and its moon do not orbit in a simple hierarchy. Instead, they rotate around a shared center of mass located in space between them. This creates continuous gravitational interaction, a constant tidal flexing of Pluto's interior. Over immense timescales, this flexing generates heat. And that heat may be one of the key mechanisms sustaining a subsurface ocean. What appears to be a frozen world is actually a system under slow but continuous internal stress. A world that refuses to fully settle into geological silence. Naturally, this raises a deeper question. If a subsurface ocean exists, could anything survive within it? Some researchers cautiously suggest that microbial life is not impossible. Not complex ecosystems. Not surface organisms. But simple, resilient microbial systems adapted to extreme isolation. Life without sunlight. Life without an atmosphere. Life without direct solar energy. Only chemistry, pressure, and time. If such life exists, it would fundamentally reshape biology. Because it would mean life is not dependent on warmth or proximity to a star. It would mean life is adaptable far beyond current assumptions. Pluto's atmosphere adds another dimension to this mystery. Extremely thin and fragile, it is composed mostly of nitrogen, with traces of methane and carbon monoxide. But despite its weakness, it is chemically active. Ultraviolet radiation from the distant sun interacts with these gases, triggering reactions that produce complex organic molecules known as tholins. These molecules gradually settle onto Pluto's surface, giving it its reddish coloration. More importantly, they represent prebiotic chemistry, the chemical building blocks that can lead toward life. Infrared observations have also revealed subtle temperature variations across Pluto's surface. Certain regions appear slightly warmer than expected, hinting at localized internal processes beneath the ice. Nothing dramatic, but persistent enough to suggest internal complexity is still active. Even Pluto's largest moon contributes to this evolving system. Its surface contains enormous fractures and ancient geological scars, indicating it too once experienced internal activity. At its poles, reddish deposits have been detected, likely material transferred from Pluto's atmosphere and frozen onto its surface. This suggests a slow exchange of material between the two bodies. Not a static system, but an interacting one. A paired evolution. When viewed in the broader context of the Kuiper belt, Pluto becomes even more unusual. Most objects in this distant region are small, cold, and unchanged since the formation of the solar system. They are frozen remnants of early planetary formation. But Pluto does not behave like them. It shifts. It evolves. It shows signs of internal and surface activity. It refuses to remain static. This forces a larger question. If Pluto is active, how many other distant objects are the same? How many icy bodies beyond Neptune contain hidden oceans beneath their surfaces? How many worlds have we misclassified simply because they are too far away to study in detail? Future exploration may eventually provide answers. Orbiters capable of penetrating ice layers with radar. Landers analyzing surface chemistry in situ. Long-duration probes studying atmospheric and seasonal changes. Each designed to uncover hidden layers of distant worlds once thought simple. Some scientists even speculate about weak magnetic effects or internal shielding mechanisms that could help preserve Pluto's atmosphere against solar wind erosion. If true, this would suggest a more stable and complex internal system than previously imagined. What was once dismissed as a frozen, lifeless remnant at the edge of the solar system is now being reconsidered as a dynamic, layered world. Not a failure of classification, but a failure of early understanding. Pluto challenges the definition of what a planet should be. It expands the boundary of habitability. And it forces us to accept that complexity does not require warmth, proximity to a star, or surface activity visible from afar. It can exist in darkness, in isolation, at the farthest edges of the system. Pluto is no longer just a demoted planet. It is a reminder that discovery is often not about finding new worlds. It is about realizing that familiar ones were never truly understood. And beneath its frozen surface, the real story may still be unfolding, slowly, quietly, and far more importantly than we ever expected.